Algebra II 3.8, Determine linear functions and data points. Now, if you haven't seen the previous videos for Chapter 3, you might get confused, but you can go to this video's description and click on the link for Algebra 2 playlist and find all the Chapter 3 videos that you may have missed, okay? We can find a linear function and use the equation to make predictions. We can use a linear function as a mathematical model of the situation. Now, not all situations can be described by linear relationships, but when a relationship is linear, we can use the line of best fit to make predictions. So what they're saying is, if we graph data and we make a line, we can predict what is in between here, okay? We can predict points that are in between here, in between the given data. So crickets are known to chirp faster at higher temperatures and slower at lower temperatures. Well, that means this number of chirps is a function of the temperature. For our x values, that's going to be a t for temperatures in Celsius, and c is going to be our y values, the number of chirps per minute. And that makes ordered pairs here, doesn't it, this data? We can use this data collected in a table to predict the number of chirps per minute for 18 degrees Celsius. So that would be in between here, wouldn't it? So it's not graphed and it's not in our table, but we can use the values here to predict what 18 degrees Celsius would be for the number of chirps. The first thing we do is plot the data from the table to see if the linear equation gives an approximate fit. So here's all the points plotted. We make the graph with a t-axis for temperature, going this way, and a c-axis for the chirps per minute. I'll show you a closer view of this, see? So the chirps per minute are going in increments of 10, and the degrees are going in increments of 5 along here for temperature, okay? The data values lie almost on a straight line, don't they? They're a little bit off, but we learned in 8th grade math that if there's one point that's a little outside here, then we need to have another one a little point outside on this side, okay? And we come right up in between them. Well, this means we can use a linear function to model the situation. We're going to use two of the data points to find a two-point equation. So we're going to use for x1, y1, the 6 and 11, and for x2, y2, we're going to use 20 and 109. Since the line goes through them is very close to the line we fit over the domain of the data, I'm going to put it in point-slope form, okay? So we're going to use that point-slope form of an equation. So instead of y, remember, we're using c, and instead of x, we're using t. So this is what we're going to end up having in point-slope form, okay? So it'll be c minus c1 instead of y minus y1, and then we've got c2 minus c1 over t2 minus t1, see, for the x and y, to find the slope. And then we need to multiply it by this t minus t1, okay? So we plug in our values from these points. Remember, these are the 1 values, these are the 2 values. So we've got c minus 11, because that's our y1, isn't it? Our c1. And that's going to be 109 minus 11, the y2 minus y1, or c2 minus c1. And we've got 20 minus 6, don't we? So that's going to give us 98 over 14. Now we need to multiply it and distribute it into the t minus 6 over here, see? Just like in point-slope form, all right? So 98 divided by 14 is a 7, nice and even. And now we're going to distribute the 7 to the t and to the negative 6, and we get c minus 11 equals 7t minus 42. So I moved it up over here. C minus 11 equals 7t minus 42. We need to isolate this c, so I added an 11 to this side and to this side. That created a 0 pair here, and I isolated the c. And we get c equals 7t minus 31 when we add the 11 to this side. Now what we have to do is plug in that 18 degrees Celsius for the t, as c equals 7 times 18 minus 31. That gives us 126 minus 31, which gives us 95 chirps per minute at 18 degrees Celsius. And that would put us about right here on the chart, see? So we had these other data points, and we used them as a guide to find information that was in between, see? You can also do it for information that's outside the given. We could do it up here. We could use this as a trend line, couldn't we? All right, we talked about trend lines in 8th grade. Okay, so this one's a little bit different. This table lists the friction, the wind resistance, of a car at various speeds. Can we predict the resistance at 50 kilometers per hour? So here's our speeds, S, that's going to be our X values, and our resistance in kilograms, that's going to be our Y values as R, and here's our ordered pairs that we can graph as points on the line, okay? And we need to find 50 kilometers, and that's going to be in between here, isn't it? So we know that the resistance is going to be somewhere between 15.1 and 30 to be correct, because 50 is in between 45 and 52. When we graph this data, we find it doesn't make a straight line. It kind of goes straight to here to the 40, but then it shoots upwards like an angle. So it seems that there's two linear parts. There's this one and this one going upward, and it breaks at 40. So it's almost as if we've got two lines, see? See that? It's almost like there's two lines here. There's this one and this one. So for the speeds from 0 to 40, like from here to here, that's one line. And then from 40 and higher is another line. So what we can do is two different equations. We can do one for the speed that's less than or equal to 40, and another one for the speed that's greater than or equal to 40. So what we do is we put them in that point slope form, and we're going to use R for Y and S for X, and we do our math, and we plug in our values. We're going to use the points 10 for S1 and 3.2 for R1, 40 for S2, and an 8 for R2. We find the slope, and we get 8 minus 3.2 over 40 minus 10. That gives us 4.8 over 30, or 0.16. We plug in this 10 for the S1 value, and that would have been the X1, wouldn't it? But we're using S for speed. Then we distribute the 0.16 into the parentheses, and we get 0.16s minus 1.6, because that moved the decimal point over, didn't it? And now we need to isolate the R, so we add a 3.2 to each side to create a zero pair here, and we get R equals 0.16s plus 1.6. So any speed that's 40 miles an hour or less, we can plug in for S. So this is only for the 40 mile an hour or less, 40 kilometers per hour or less, I'm sorry. So this is the speed that's under 40, okay? So in order to do the over 40, we picked some over 40 kilometers per hour speeds, okay? So I picked 40 and 8 and 52 and 30, all right? So I picked this pair and this pair, all right? And I plugged them into the point slope form, and I found the slope was a 30 minus 8, and 52 minus 40 for these values underneath here, which would be the X values, wouldn't it? Here's the X1, which is going to be S1 in this case, and I did my subtraction. 30 minus 8 is a 22, 52 minus 40 is a 12, and then when I did the division, 22 divided by 12 is 1.833333, and the 3 kept going on, so I put the bar over the top, which means now we have to use approximate, don't we? Now I have to distribute this 1.83 into the parentheses, and I got 1.83s minus 1.83 times a negative 40 is a negative 73.2. We need to isolate the R, so we're going to add 8 to each side to get rid of this minus 8 here, and that gives us R is approximately, because of that 333 thing at the end of this decimal, so it's approximately 1.83s minus 65.2. So this is the equation we can use for when it's over, the speed is over 40 kilometers per hour, okay? So now all we have to do is substitute 50 for S. Because remember, at the beginning of the problem, we're trying to predict the resistance at 50 kilometers per hour, okay? So we're going to plug in the 50 where the S is, and we get 1.83 times 50, which gives us 91.5. We subtract this 65.2 that we got over here, and we find out the resistance is approximately 26.3 kilograms. See? So we ended up using two different equations. Now, a nonlinear function is probably going to fit this data better and would be better. But I just wanted to show you that if you've got a graph and it's kind of L-shaped, you could use it as two different equations, see? And just pretend it's two different lines. And just use one for less than and the other one for greater than, see? All right, our next video is 3.9a. We're going to talk about step functions, greatest integer functions, and absolute value functions. I'm going to add this video to the Algebra II playlist so you can use it to study. That's going to be in the description of this video. And, of course, the topic we're covering is graphs and linear equations, so the playlist of Chapter 7 from Algebra 1 will be in here too for you to use to study, okay? Because there's a lot of similar videos from that chapter in Algebra 1 about what we're doing here, all right? Okay, I might even put something about trend lines from my previous videos into the description to help you, okay? I'll see you next video. Bye.